and Debye model work and fit well with the experimental data, and both experimental data and Debye theoretical data give CV proportional to t power of 3. Okay, so this is for Debye model, and then this is the experimental result for KCl, potassium chloride, and then this cross one is for copper. So from this graph, we can see that Debye model actually quite successful. Okay, so this result for low temperature. For high temperature doesn't matter, it will just go with 3 and Kb. Okay, but here we have two lines, right? One cross the zero, one doesn't cross the zero. Copper, it doesn't cross the zero, and then KCl, it cross the zero. So I will explain this in the next slide. For KCl, the potassium chloride, the CV over T proportional with T power of 2 through the origin, and therefore the Debye law of T power of 3 is obeyed. For copper, the CV over T proportional to T power of 2 does not go through the origin, and therefore is given by this equation. Okay, so the difference here is that you can see here we have crossing here. So the crossing is at A lah. This point we consider as A lah. This point we consider as A. So CV over T versus T squared. So CV over T versus T squared, the graph. So CV over T equal to cross A plus BT power of 2 because versus T squared. So when you move the T to the right hand side, you will get CV equal to AT plus BT power of 3 for copper. But for potassium chloride, is CV over T equal to BT power of 2, then CV equal to BT power of 3. This is for KCl. This is for copper. So you can see there's one difference. Here we have AT, but here we don't have AT. Why? Because this AT is the specific heat contributed by the electron gas, and then the BT power of 3 is the specific heat contributed by the lattice, the lattice vibration. So for both KCl and copper, both have T power of 3. Okay, so both have the lattice vibration. Of course, all the material have lattice vibration, but only copper, which is a metal, have the specific heat that contributed by the electron gas. Why? Because copper has free electron gas. Free electron is a metal, the free electron conductor, electric conductor. But KCl is not a good conductor because it don't have the free electron. When it don't have the free electron, definitely it does not have the specific heat that contributed by the electron gas. Okay, so in this chapter, we have discussed the specific heat capacity that contributed by the lattice, the phonon. So in next chapter, we're going to discuss the specific heat that is contributed by the electron. Okay, so we will only discuss this AT in the next chapter. Okay, that's all for specific heat capacity. Debye model has actually successfully explained the model of the specific heat capacity. So now you want to move on to the thermal conduction. Okay, so the flow of thermal energy in the crystal is through the phonon. Okay, so basically the lattice vibration will transfer the heat from one lattice vibration point to the other lattice point. It also can be transferred through the photon. It also can transfer through the free electron. But photon, free electron, and pair of electron hole are not in this chapter lah. Okay, but free electron will be discussed in next chapter. For the example, KCl. KCl, the thermal conductivity, the thermal conductivity only involve phonon. But for copper, the thermal conductivity involve both phonon and free electron. Okay, but this chapter will emphasize on phonon, therefore we only discuss about the phonon. So in matter, the electron are the main component. In non-matter, the lattice vibration or the phonon are the main component, except at a very high temperature where the photon become the main component. We'll discuss the thermal conduction by phonon current, the heat when there's a finite temperature gradient. Okay, so let's say I have one material here. So when I hit the end of the material, then the heat will transfer from the end to my hand. Okay, so this is the heat transfer. So consider the rod shown below, this one, the heat, the rod. So when I hit at one end, the phonon gas will flow from one end to the other end, to my hand just now. Okay, the heat will transfer from this end to this end, just like this shape, just like this figure, from T1 to T2. Okay, and the temperature of T1 is larger than T2 because the heating source is here, and the heat transfer from the higher temperature to low temperature. So heat will flow from T1 to T2, here to here. Then the relationship between the heat current density per unit area Q and the temperature gradient dT over dS is given as this equation. So Q, the heat current density per unit area Q, equal to negative K times dT over dS. Okay, K is the thermal conductivity. So why we want to put the negative here? Because we are referring the T1 to T2. So from the hotter one to the colder one, you'll get the negative result. So in order to get a positive Q, then we just substitute we just add in the negative sign here lah. So the proportionality constant K, known as the thermal conductivity, is a measure of the ease of transmission of heat across the bar. And the minus sign is induced so that the K is a positive quantity. Heat may be transmitted in the material by several independent agents. In matter, for example, the heat is carried both by the electron and phonon, although the contribution of the electron is much larger. In the insulator, on the other hand, heat is transmitted entirely by the phonon, since there are no mobile electrons in this substate. Here, we consider only the transmission by phonon in this chapter. So since K has a positive value and dt over dx has a negative value, a negative sign is included in the equation so that Q is positive like what I explained just now. And phonon can be assumed as a gas where all particles travel with the same speed, and therefore we can use the kinetic theory for a gas, this equation. Okay, so from this equation, Cv is the specific heat per unit volume, constant volume. Then V is the phonon average velocity, and L is the phonon mean free path. So the mean free path is defined as the average distance between two consecutive scattering events. So that the mean free path equal to V times tau, where tau is the average time between the collision, which is called the collision time or relaxation time. So here I give you some example, a table that show you some value of K and L. So L will increase when T decrease. L and K are dependent on temperature. Then these are the example of variation of L and K with temperature. Yeah, and that's all for this chapter 10. Thank you for the attention.